In this video, I am introducing the idea of the atom. So atoms are understood to be one of the most basic building blocks of matter. And matter can be gases, liquids, or solids, right? And even there's a fourth sort of phase of matter that's referred to as a plasma. That's pretty interesting. Like, for example, the sun is a sort of plasma system. Okay, so likely you've heard of atoms. It tends to be one of the most important concepts taught in science classes. It's an old idea, maybe back in the time of the Greeks. Let's see, famously, I think Aristotle, I'm just going to quickly look. I've got the book open next to me. I think Aristotle, long ago had a pretty interesting point of view that stuck around for a long, long time, that that there were only four basic types of substances: earth, wind, fire, and water. Yeah, so that was Aristotle's long ago view, and it stuck around, and people thought there was something to that. But as people were able to pay attention to nature in deeper and more, honestly, slightly more technological ways, somewhere around the 1800s, people could use microscopes and look really close at matter and realized that like even solid things that don't seem to have any internal motion, was made out of materials that, or made out of small bits that were very lively, right? So yeah, so this became this atomic hypothesis that matter is made out of these basic building blocks, right? So it goes without saying that every atom is small. And in fact, in your reading, you should try to, or you should work hard to understand precisely how small, right? It is smaller than cells, right? Cells in living tissue, like skin cells or hair cells. Of course it's smaller, right? Because cells themselves are made out of atoms, right? So it's really small. Each atom is very, very small. Oh, this is a spell check issue. I meant to say, so there are many, it's going to do it again, yep. So there are lots of atoms in nature, right? Numbers that you'll see thrown around are numbers that look like 10 to the 23. And this is just in any sort of macroscopic sample of material, like 1 gram of a substance. You could consider like a little cube of water, 1 centimeter on a side, right? In there is something like 10 to the 23 atoms. Actually, yeah, you could argue that this number 10 to the 23 represents the number of separate atoms that make up 1 gram of sort of a standard material. So every atom is individually very small, and in nature there's just millions and trillions and billions and 10 to the 23s of these atoms around. But I think it's very interesting to point out that there are only a little more than 100 possible different atoms. And what I mean by that is atoms that are constructed of different numbers of things. Wow, I'm kind of messing up here, but the point is there is a organizational chart called the periodic table, and on this periodic table is only about 18 different types of atoms, right? So, and that's all there is in all of the universe, right? And that's a really important thing that scientists, chemists, physicists, natural philosophers have found out about nature. Nature has lots and lots of atoms, but there's only about 118 different kinds of atom, right? So it's sort of similar to our 26-letter alphabet, right? With 26 letters, we can construct almost, well, I don't know how many words in the, for example, English language, but with our 26-letter alphabet, we have many, many, many possible words. And from those words, we have sort of uncountable possibilities in books that you can write, or sentences that you can write with those words that are actually made out of letters. And there's only 26 letters. And that's the kind of the analogy. We only have 100 atoms, 100 different kinds of atoms. But from that, you can make many, many, many different kinds of molecules and compounds that can connect together in uncountable combinations and make things like DNA molecules and diamond crystals and salt on potato chips, right? So paint, semiconductor chips, parts of people's hair, everything, right? Pieces of the sun. So moving on, there is, for atoms, a very generic structure. That is, all 118 of these different types of atoms has a common generic structure. And what you're going to see is that each of these little atoms is a little system of particles. Particles that you've heard of, like the electron, the proton, and the neutron. So these are little systems of particles. So the generic structure has a single positively charged nucleus, which is surrounded by possibly multiple negatively charged electrons. And then the nucleus itself, this little positively charged central thing, is a grouping of neutral neutrons and positive protons. And it turns out that the nucleus is where all of the mass of the atom essentially is. Electrons also have mass, but they have way much less mass than protons and neutrons. So most of the mass of an atom is down in the middle of the atom in the nucleus. You'll see that sometimes these neutral neutrons are labeled like this. So this is N0, right? So the 0 stands for no electric charge. The protons sometimes are described this way. So there's a little P stands for proton, and the little plus sign, which I was having a hard time drawing very well, is up in the corner. So this is the proton. And then electrons are often described this way, E for electron with a little minus sign. And then I'll point out that there is an entire big piece of physics, a big corner of physics. A large part of doing physics is to do nuclear physics. And in nuclear physics, you can study issues associated with nuclear weapons, nuclear power, nuclear energy. It's a big one, maybe for our future. Nuclear waste. Yeah, and also nuclear fusion, nuclear fission, reasons for why stars have so much energy or can emit so much energy out into the rest of the universe. So atoms, a long time ago, people developed a model for the atom that was something like little satellite orbits. And so what this looked like was there was a central nucleus that was positively charged, and surrounding that nucleus were little orbitals where electrons were moving around, and the orbitals tended to be drawn like this. Oops. And it's something of a cartoon model, right? And so this was a model. It was a sort of mechanical looking model. Negative charge and positive charge are attracted to each other, kind of like gravitational interactions between masses that give rise to moon satellites going around central planets or planets going around a central star, right? In this case, we have this very massive nucleus, and then it's surrounded by orbiting charged, oppositely charged particles, right? So that's an old model. It turns out that this model is not really the best way to think about stuff, but it's a good starting point. A better, more modern model, which is informed by the fact that nature at atomic sizes is very quantum mechanical. So in this course you will learn some conceptual ideas from quantum mechanics, and here actually is the first conceptual idea that the electrons, they exist in more of instead of these orbitals where you could say that the trajectories are well defined, right? And the particle just goes around in an elliptical orbit or a circular orbit around the nucleus. The quantum mechanical point of view is that actually the electrons, they exist in what are called orbital shells around the nucleus, and the electrons occupy these shells in somewhat vague clouds of probability. That is, the electrons have locations that are governed by probability, that is pure randomness and statistics and statistical distributions. But so this is the more modern model. There is still this nucleus down in the middle, but surrounding it is this sort of vague cloud where the electrons can live, and this cloud itself is negatively charged, right? So cloud of electrons. And yeah, so this is the more modern point of view on what atoms are like. Okay. All right, so in other videos, I'm going to explore other issues associated with thinking about matter as groupings and collections of atoms.